Cool. Okay, fantastic. Well, welcome everybody. Thank you all for coming. This is Karina Kai's PhD defense, almost a senior thesis defense. I don't know where that goes. PhD defense. So thank you for all being with us this Friday afternoon to watch. Karina got her undergraduate degree at Princeton in mechanical engineering, became a mechanical and aerospace engineering, probably officially, I guess is the title, and came to Caltech in control of dynamical systems, and has been working in a number of different areas over the years, some sub-fraction of which she may tell us about. So some work that she did initially in areas around semantic estimation and other things, and then more recently kind of transitioned from that into areas around rules of the road and thinking about how to think about autonomous systems, all related to autonomous systems and kind of safe and interpretable design of those systems. And so with that, I will turn it over to you, Karina, to tell us what you've been doing in your PhD.
Okay, thank you, Richard, for the intro. Today, I will be talking about safe and interpretable autonomous systems design, behavioral contracts, and semantic-based estimation. My PhD advisors are Richard Murray and Soonjo Chung, and on my committee are Manny Chandy and Joel Burdick. So we are on the verge of experiencing an integrated society, one in which autonomous robots will become a part of our everyday lives. We can already see how robots are transforming industries ranging from transportation, warehouse robots, security robots, surveillance. These are just a few out of many, many more industries. So robots offer a lot of possibilities in enriching our daily lives. But before we introduce them into a setting where they interact heavily with humans, we have to make sure that they're safe. So there's low risk that they cause injury or harm to humans, and that they're interpretable. We can explain their behavior and we understand when agents will succeed or fail. Unfortunately, the Uber and Tesla crashes in these past few years are kind of grim reminders that the algorithms that we're designing have very real and potentially fatal consequences. So it's our responsibility as researchers and engineers to make sure that we're designing algorithms in a way that are safe and interpretable. So the goal of my thesis is kind of how do we introduce frameworks for designing algorithms in a way that's safe, productive, but also interpretable. So here's kind of the outline for my PhD presentation. Basically, every kind of autonomous vehicle has this autonomy stack, which has 4 different layers. The sensing layer is basically where the agent uses its sensors to take data about the environment around it. The perception module is where the agent interprets the sensory data. So it tells the agent what is around it and how far away those agents are. The decision-making module takes as input what's around the agent and chooses what action it should take. And in the controls layer, it kind of translates that decision into hardware. So my talk is divided into these 2 different parts, and they kind of are pretty independent. So in the first part, I'll be talking about how do we design the decision-making module for for autonomous vehicles in a way that's safe and interpretable. So I'll be introducing this framework called behavioral contracts to do that. And in the second part of the talk, I'll be talking about the perception module. So how can we leverage information from object classifiers so we can improve the vehicle's ability to figure out where it is. And these frameworks that I'm going to introduce are meant to kind of be generalized to any kind of autonomous robot. But in the first part, I'll kind of describe the use case of self-driving cars. And in the second, more we'll focus on drones. So here is the decision-making problem. And here we are trying to design agent behavior in a way that's correct. And by correct, we mean that it's safe and the agents are able to make progress. Unfortunately, this problem is largely unsolved currently. And the reason for this is because it's very challenging to design agent behavior. So one of the reasons is that the agent behavior, when it's interacting with other agents, is highly coupled with the behavior of other agents. And you run into this thing called unbounded rationality. So here, if you're kind of the green agent, then the green agent is thinking about how the blue agent will react to it. But the blue agent is also thinking about how the green agent is thinking about how the blue agent will react to it. And then you get this kind of infinite line of reasoning that can exist between different agents. So that's unbounded rationality. Also, this problem grows very computationally intractable very quickly because the agents are kind of using this joint action space to reason about what action they should take. And that joint action space grows exponentially in the number of agents. And then finally, if the environment is too complex and kind of the uncertainty about other agent behavior grows too large, then the only safe thing that an agent can do is to freeze. And that's not useful for us. So in the literature, there's a bunch of different approaches on how to kind of design agent strategies or behaviors. And I kind of categorized them into these two different groups. We have the individual approach, where the idea is you want to model the interactions between these different agents and then design a strategy for an individual agent. And you can kind of see this being done in the formal methods community with minimum violation motion planning and rule books. And then also in the POMDP community with by modeling agents as players in these Markov games. And finally, you have these data-driven methods where you're trying to learn the interactions or the interactive behaviors between different agents and then design a strategy based on that learned model. A little bit less explored is this collective approach. So in the collective approach, you essentially have a bunch of agents and you're trying to define how you can minimally constrain the behavior of every agent in a way so that when you put these agents together, they act in a nice, coherent way, and in particular, they're safe. So that idea was kind of introduced in 1995 with the name of defining social laws or conventions for a collective set of agents. And then more recently, there's been work on kind of defining how agents should maintain some distance among each other in responsibility, safety, sensitivity, and also these kind of auction-based methods to resolve conflicts among agents. So even though we haven't solved this problem for robots, humans are actually really great at solving this problem. So here we can see a really complex intersection in Swindon, England, and there's a bunch of agents interacting with one another in this really complex setting. But we can see that all agents are kind of safe and they're able to make progress towards their destination, which is really impressive. And if we kind of look closely, we'll actually see that all agents are following these simple behavioral rules, like maintaining distance, trying to avoid collision, and then following some traffic rules, like yielding to other agents and following lanes. So this video kind of hints at why it might make more sense to think about agent behavior by designing a set of rules for a collective of agents to follow instead of designing a control strategy for every individual agent. And that's kind of the theme of the work that I will present to you in this presentation. So this work was done in collaboration with Tung Fan Min, who was also a researcher in Richard's group. And so our approach was inspired by this idea of assumed guarantee contracts. And in an assumed guarantee contract, you have a system and an environment. And the contract says the system will guarantee its specifications as long as the agents in the environment are kind of satisfying its assumptions specified in the contract. So kind of a more intuitive way to think about this is under the assumption that all other agents are not acting intentionally to collide with my agent, I can guarantee that my agent will not collide with other agents. So that's kind of just an intuitive example. And in the context of self-driving cars, we introduced this specific contract. So we're saying we guarantee that the system will act according to this set of behavioral preferences, as long as the agent is kind of, all other agents in the environment are acting according to some set of behavioral preferences. And a natural question to ask is, what makes a set of behavioral preferences correct? Or what are we looking for in agent behavior? And these are just kind of a list of properties that we're seeking when we are defining agent behavior. So in the first part of the talk, I'll cover these two properties. So I'll define a behavioral profile, which is a way that agents are using to select actions so that it's interpretable and scalable. And then I'll kind of extend the definition of profile so that we can kind of capture these properties as well. So when we're thinking about designing a behavioral profile, we first ask the question, what are the rules that agents should follow? And these are kind of the first set of rules that come to mind: safety, lawfulness, progress, comfort, fuel efficiency, and courtesy. So these are just a few examples. But a lot of the times, agents are kind of choosing to take actions that might only satisfy some subset of specifications or rules. So because they're only satisfying a subset of rules, it becomes important for us to kind of define some ordering or some level of which rules are more important or less important than others. And that's why we define some kind of mathematical structure on these rules. And we want to define the structure in a way so that agent behavior is interpretable and it scales well in the number of rules that we have. So here's just a diagram of what the behavioral profile looks like. So you can think of it as something the agents are using to decide which action it ultimately wants to select. So in its given time step, there's a set of actions that it's trying to choose from. And then the behavioral profile will kind of inform the agent on how it should decide which one to ultimately select. And in the next few slides, I'll be walking you through each of the elements of the behavioral profile and kind of show you why and how we designed it in that way. So the perception and prediction problem is a really challenging problem, but we didn't want to kind of address this problem in this work. So we kind of abstracted it away into this thing that we call the oracle. And you can kind of think of the oracle as this all-knowing perception or prediction system. So we have this set of actions, and the oracle is able to say, if we take this action at this time, then it'll tell us which subset of rules will be satisfied when we take that action. So essentially, the oracle is mapping actions to which subset of rules that will be satisfied when taking that action. And here we can see that action 1 maps to safety and progress being satisfied, but not lawfulness. So now we basically have a subset of rules that we're choosing from instead of actions. And the role of the profile is to select which subset of rules is the most important to satisfy for the vehicle. And that's kind of the role of this profile. And as the designer of this profile, we have to figure out how we want to kind of design the ordering of subsets relative to one another. The kind of most simple way you can think of defining this profile is by brute force. So you're saying, let me kind of list out all possible kind of subsets that can exist or be satisfied by the vehicle. And then let's manually rank how every subset of rules kind of is ranked relative to every other subset of rules. As I was saying, we want to design the profile so it's interpretable and well-defined. So that means that, and it is well-defined because we know why we chose this subset of actions when we kind of have this total order on the subset, on the power set. But this kind of method of defining the profile doesn't scale well in the number of rules. And also it's not intuitive for us to kind of design exactly how every subset of rules should compare to every other subset of rules. So we want to do something better. And here we kind of propose the idea of having a profile with a partially ordered set. So here we're saying, what if instead of defining how every subset compares to every other subset, we're saying, what if we can just define how one rule kind of ranks relative to another rule. So here we're saying safety should be prioritized over lawfulness, lawfulness should be prioritized over courtesy, and so on. And basically each of these comparisons induces a partial order on the set of rules. And then what we're saying is, can we define some function on this partially ordered set so that it gives us a way to rank subsets relative to one another? And in particular, it admits this unique weak order. So weak order just means that we have a ranking of subsets relative to one another where some members can be kind of tied with one another. And we also want the function to map to something unique, meaning that there's only one way to interpret how these subsets should rank relative to one another when you're given this partially ordered set. not all partially ordered sets kind of have this consistent evaluating function defined on it. So it's necessary for us to define what additional mathematical properties we need on this partially ordered set so that we can define this kind of function that tells us how subsets should be ranked relative to one another. So that's what these two theorems capture. So theorem 1 says that a finite partially ordered set of rules has a consistent evaluator if and only if it can be partitioned into a set of n maximal antichains such that A, the maximal antichains can be assigned ranks in such a way that the partial order is respected. So what this means is that we can partition this partially ordered set into a set of maximal antichains and assign ranks that respect the partial order. So that means if this node is more important than this node by the partial order, then it has to be assigned a rank that has greater value than this node. And then also B, for each specification, there exists a maximal chain containing it of length n. So that means for every node, it's part of a maximal chain that has length n, which is the number of partitions that this partially ordered set has kind of been partitioned into. And then it's an if and only if statement. So that means that if we can kind of decompose the partially ordered set in this way, then we can also define this consistent evaluating function. And theorem 2 says the decomposition in this theorem is unique. So now I kind of want to show you what the theorem means in the context of an example. So here we have this partially ordered set of rules, and it satisfies, it's kind of easy to see that it satisfies these two criteria in the theorem, which means that we can define some consistent evaluating function that tells us how to compare subsets of rules to one another. So here I'm going to show you kind of how exactly we define that consistent evaluating function. So how we compare two subsets relative to one another. And the way the function does this as it's defined is basically here we're comparing action 1 and action 2. So action 1 satisfies this subset of rules, and action 2 satisfies this subset denoted by the green squares. And it counts how many rules are satisfied in every layer of the partially ordered set. So here 1, 1, 1, 1, 0, 1, 0, 0, and 2, 0. And then it does a lexicographical ordering. So it keeps on going down this ranked list until there's a mismatch, and then whichever kind of action has more is the winner. So, or is basically valued higher than the other action. So in this case, action 2 is evaluated to have greater value than action 1. And basically, if we do this for all subsets, then we can figure out which subset is kind of the highest value and valued and choose which action to take. So this kind of defines the process that agents are using to select which action they want to take. But we want to zoom out back into this multi-agent setting, and particularly in the context of these assumed guarantee contracts. So if we think about how these profiles fit into these assumed guarantee contracts, we can think about the assumption as on all other agents as that they have some profile that obeys some set of profile constraints. So here we can say that for all other agents in the environment, they should always prioritize safety over lawfulness. And then the guarantee in this contract is that the agent is kind of satisfying or choosing actions according to this one specific profile. And unfortunately, when we put this kind of way of choosing actions into a game setting, we see its limitations. So in this scenario, we have two agents, and each agent is kind of operating or choosing actions in accordance to its profile. And then when we kind of use the consistent evaluating functions to evaluate these joint actions, we get these values. And then basically higher values mean that it's more preferred. And what we can see is that there's actually two actions that are Nash equilibria, meaning that for each of these kind of joint actions, neither agent has an incentive to switch strategies. But what that means is that because the agents aren't actually coordinating their behaviors, it's kind of ambiguous as to which action the agent should take independently of each other. So because this is the case, it's kind of, it means that we can't make guarantees about agents being safe or agents making progress. So that motivates why we introduced this idea of behavioral protocols. So far, just to summarize, we've defined a behavioral profile, which is what agents are using to select actions in a way that's interpretable and scalable. But now we want to have agents selecting actions according to a profile, but then introduce some additional rules that say or tell the agent whether or not it's actually able to take the action it intends to take. And in kind of adding in these additional constraints, we have it such that we can guarantee that all agents are safe, meaning that they don't collide with other agents, and that all agents are able to make progress towards their destination. So before introducing the protocol itself, there's some kind of overhead that I have to get through and define. So I'll first define this quasi-simultaneous discrete game and the road network that we're assuming agents to be playing on. And then I'll introduce the agent protocol, which is defining the strategy agents are using to select their action. And if all agents are kind of operating according to this protocol, then we get these really nice properties about agent behavior. And I'll kind of walk you through proofs of safety and progress and show the results in simulation. So here is an image of the road network. And here I'm going to kind of parse through each of these elements with you. So there are sync nodes, which are nodes that the agent can kind of leave the road network from. And there are source nodes, which are where agents are kind of spawning into the road network from. There are also intersections, which are kind of intuitively defined as you would think they would be defined. And they're kind of governed by these traffic lights. And then we can also decompose this road network into lanes. So lane is kind of a set of grid points that are either within a row or a column. And then there's the bundle. So a bundle is a collection of lanes that are all kind of neighboring and going in the same direction. And then we also have road segments. So road segments are bundles that have been partitioned by the intersection. So this is a road segment, and then also this is a road segment. And basically each of these grid points has a legal orientation associated with it, which is denoted by these arrows. And then now I'll introduce the game that the agents are kind of playing according to. So we call it the quasi-simultaneous discrete game. And it is essentially the same as a turn-based game, except that the turns are not defined randomly. Instead, there's kind of, the turns are kind of determined by what state the agents are on in the road network. So the way we kind of assign precedence or turns in this game are we divide this road network into bundles. And then for every bundle, basically any agent who's kind of longitudinally ahead of any other agent gets to take their action first. So this graph kind of denotes which agent gets to go first in this bundle right here. And then this graph kind of represents the precedence or turn order agents get to take in this bundle. And then basically the precedence between different agents is incomparable. So it doesn't really matter which agent in which bundle goes first. So now I've introduced to you the game and the road network that agents are operating on. And I want to be clear that right now we're only considering one single agent class, and that agent class has these specific properties. In particular, each agent has a token count, and this token count kind of represents how many times an agent hasn't been able to make forward progress towards its destination. And every time it does make forward progress, this token count resets to 0. And we're assuming that agents kind of have access to the token counts of other agents. Each agent also has an ID and a goal assigned to it. We also establish discrete dynamics. So an agent has a min and max acceleration, a min max velocity, and also these different maneuvers. So these take on integer values. And then it also has these left-right turn maneuvers, left-right lane change, and straight actions. And basically, whenever it takes these kind of maneuvers, it'll occupy the grid points that are in gray. And also, it doesn't make sense for us to assume that agents have access to all information about all other agents in the road environment. So we say that each agent is constrained to reason only about agents within its bubble. And this bubble is defined very carefully, and in particular in a way where agents can make sure that they'll be able to take actions that are safe with respect to the other agents. And probably the most important kind of feature of each agent is that it has this backup plan action. And you can think of the backup plan action as the agent kind of applying maximal deceleration until its velocity gets to 0. And because of the way the dynamics are defined, it actually might take multiple time steps for the velocity to reach 0. And when we talk about safety, we're going to say that we're trying to preserve this backup plan action, the safety of this backup plan action for every agent in the road network. And I'll talk about that a little bit more later. So now I've kind of finally got to the meat of this work, and that's kind of this idea of how do we define agent behavior in a way that lets us guarantee safety and progress. So the first half will look very familiar. The first kind of step of this protocol is kind of doing this local precedence assignment. Because this is a turn-based game, agents have to know which order turn it takes in the game. So basically agents ahead of it have higher precedence or get to go take their turn first, and then agents kind of behind it will take their turn after. And then agents use this profile. So this is exactly the profile as I had defined in the first part of this talk. And here we define a profile with 10 specific rules. So the top layer has to all do with rules related to safety. The second layer relates to lawfulness. And then the third and fourth layers relate to progress. And the agent is essentially figuring out which action it intends to take using this profile. So there will be a set of actions, and it evaluates these set of actions and ultimately decides which one it wants to take. So that looks very similar to the first half of this talk. But as I alluded to, that's not enough to kind of guarantee safety and progress. So in the second part of the protocol, we introduce the conflict cluster resolution and the action selection strategy. And you can kind of think of this part of the protocol as additional constraints telling the agent whether or not it has the right to take its intended action. So in the conflict cluster resolution, we have an agent kind of determines which other agents it's in conflict with. So defines when its intended action conflicts with other agents' intended actions. And then it determines whether or not it's the winner within its cluster based on token counts. So if it has the maximum token counts, then it'll win its conflict cluster. And if not, then it'll lose. And then that information kind of feeds into this action selection strategy. And you can think of the action selection strategy as a decision tree that the agents are using to ultimately determine whether they can take their intended action or they have to take some suboptimal action, which will either be the best straight action or a backup plan action. And the decision tree is kind of based on these 5 different conditions. So that's how the agent protocol is fully defined from end to end. And the thing about the protocol as it's defined is that it allows us to guarantee safety. So our safety theorem says that given all agents in the game are acting in accordance to this protocol, we show the safety property P implies always Q. Or P is the assertion that the game is in a state where every agent has a backup plan action that it's safe. And Q is the assertion that agents never occupy the same grid point at the same time, so that they never collide. And here is kind of a slide that shows a sketch of the safety proof. And we, in the sketch, the main premise of the proof is that we're kind of showing the invariance of the safety backup plan action. So each agent always has a backup plan action that they can take that will be safe. And so P is the assertion that the agents are in a state of the game where each agent has a backup plan action that's safe. And then I, this invariant assertion says that agents take actions that 1, do not collide with other agents, and 2, preserve the safety of all other agents' safety backup plan actions. And then basically if agents are taking actions in accordance to this assertion, then they'll end up back into a state in which each agent has a backup plan action that's safe. And then this invariance will always hold. And if this invariant condition always holds, then agents will never occupy the same grid point at the same time, and they won't collide. But showing safety isn't enough. And basically, you can kind of define a control strategy where agents never move and agents will be safe. So we also want to show that the way the protocol is defined allows us to guarantee the progress of all agents. But unfortunately, there's this case that occurs when where deadlock occurs. So if all agents are kind of occupying these grid points, then they enter a deadlock state in which no agent can kind of make forward progress. So we have to just define the sparsity condition, which says that the number of agents in this road network is 1 less than the number of agents in this loop. And then that allows us to have the progress or liveness theorem, which says, given the sparsity conditions hold and that all agents are selecting actions in accordance to the protocol, we can show all agents will eventually reach their destinations. So this proof is kind of based on showing that all agents in the road network will always eventually take a forward progress action. And the reason that all agents are kind of eventually taking this forward progress action are because of two features. One, that the profile has this forward progress specification, so it wants to take actions that make forward progress. And the second is that we have this notion of fairness that's defined within the tokens. So it's saying that agents with the highest token count have priority in taking their forward progress action. And I'm not going to go into the details of the proof, but the second part is kind of showing how we show all agents are able to make a forward progress action. And that's kind of based on this idea that first we show that agents on this road segment where there's a sync node will always eventually take their forward progress action, leaving clearance in this road segment. And basically any road segment that kind of depends on clearance in this road segment will also always eventually take a forward progress action. And then we can extend this to kind of any road segment on the road network and show that show the liveness property. So this is kind of the fun part, and this is how we see the protocol working in simulation. So in this simulation, agents are spawning on the left side with some random probability, and each agent is assigned randomly assigned a destination on this side of the map. And when they make it to their destination, they kind of disappear from the road network. And they have these discrete dynamic parameters, so -1, 1, 0, and 3. And basically each agent in this simulation is kind of taking actions in accordance to the protocol that I had defined. And we can see that no collisions occur. And we can see also that all agents that kind of have enough time to make it to their respective destinations by the end of the 250 time steps will make it there. And this simulation is kind of intended to show the generalizability of our framework. So the protocol is kind of defined on any road network in which the intersections are governed by these traffic lights. And each agent is operating according to the protocol that I had defined earlier. And again, we can see that no collisions ever occur. And then also all agents that kind of have enough time to make it to their respective destinations will make it to their destinations. So here's just kind of some statistical results using the simulation. So we kind of generated these 3 different road networks, and then we conducted 100 randomized trials on each of these road networks. And again, we see that for every single trial, there are no collisions. And then this is kind of the average percentage of agents that are able to make it to their destination by the end of the 250 time steps. And basically, the remainder of agents that didn't make it to their destination are kind of still on the road network by the time the 250 time steps runs out. And we can also see that the number of agents is actually much more than the sparsity condition implies. So agents are kind of still able to not reach that deadlock state, even when we have a lot more agents on the map. Okay, so I just want to summarize, and here we have that. So I've basically introduced this agent protocol, which we define for a single class of agents, which is the profile with some interaction constraints. And the great thing about the protocol is in the way that it's defined, it allows us to guarantee safety of all agents and also progress of all agents, but it's also able to do that in a way that's scalable in the number of agents and also interpretable. So, and then I also showed proofs of safety and liveness, and I showed the results in simulation as well. So now I'm kind of going to switch gears and talk about the second part of the talk, which is on the perception side of autonomous vehicles, and specifically how do we kind of encode semantic information into this perception module. And this work was motivated by this question of how does an agent figure out where it is when it no longer has access to GPS? So that's kind of called GPS denied navigation. And you can kind of see a few of the environments in which a robot might not have access to GPS. So this work was done in collaboration with Alexei Harvard from a research engineer in Sundra's group. And our approach was inspired by this idea that we have easy access to these object classifiers. And what if we had kind of a map that showed us where these detectable objects were located? Can we use that information to kind of estimate where the vehicle is located? And luckily, there's this problem called simultaneous localization and mapping, SLAM, also known as SLAM. And it solves a very similar problem. So in this problem, it's saying, given odometry measurements and visual and range measurements, can I kind of figure out or estimate the vehicle location at every time step of this trajectory, and also kind of figure out where these landmarks are located. So our idea was, what if we kind of augment SLAM with the semantic information? So how do we leverage this information from object classifiers when we're trying to do this localization problem? And this idea of semantic SLAM has been explored in the literature. So here we can see object classifiers being used to augment estimation algorithms. And in this first work, we have a kind of this detector that detects whether a robot is near a building, and that's modeled as some binary measurement with some probabilistic likelihood. And then in the second work, we have agents able to detect whether or not they see doorways or chairs, and they use this information to kind of, in this expectation maximization form, to improve the agent's ability to estimate where it is. Unfortunately, these methods are kind of not robust to false positive measurements, false positive and negatives. And then in the second class of work, we have the dual problem being solved, which is how do you kind of leverage where an object moved and how it moved to kind of improve your ability to classify objects. So the approach that I'm going to present kind of does a combination of these things and is also robust to kind of false positive measurements. So here's just what the problem formulation looks like. And here we have a vehicle kind of going through this trajectory, and it has these object classifiers. And these object classifiers are kind of telling the agent whether or not it sees the object. So a one indicates that the object can be seen, and a 0 indicates that it can't be seen. And the goal of the semantic SLAM problem is we want to estimate the vehicle position throughout the trajectory. So the first method that we use is the maximum likelihood method, and this is kind of the most common approach found in SLAM algorithms. So we're trying to solve this optimization problem, which says which trajectory and landmark positions make the most sense given the measurements that we've kind of collected over this trajectory. And this is exactly the SLAM problem, except for these semantic likelihood measurements. So we want to be able to derive what these factors look like. And luckily, this probability, which is the probability of seeing some semantic measurement given the agent state, can be derived using this confusion matrix for the object classifier. So basically, every time that we see a one measurement, we're introducing this factor into the estimation problem. And intuitively, what that means is every time you get a positive measurement, you want to prioritize or promote the agent state where that object can be seen. But a good question to ask is, what happens when you have these false positive measurements? Do you still add in this factor? And for this first method, you do. And this kind of motivates why we introduced the second method, for introducing semantic measurements. So in the second method, we have 2 layers in our estimation framework. And in the bottom layer, this is exactly kind of what we're using in method 1, but we introduced this kind of higher level estimation problem. And this kind of formulation allows us to be more robust to false positives, but it also allows us to kind of improve our certainty of object classification events. So in the next few slides, I'll kind of walk you through the bottom layer and then the top layer, and then show how they're kind of put together. So again, in the lower level estimation, we're solving a very similar problem to what we had in the first method. But here we're introducing these things called switch variables. So we're trying to, you can kind of think of these switch variables as capturing the certainty we have in our semantic measurements. So if there's kind of high certainty in this measurement, then we want to keep or include this factor in the optimization problem. But if there's low certainty in the measurement, then we kind of want to disregard this measurement. But when we introduce these switch variables, we also have to define these switch variable priors, which kind of indicate how much we should trust these measurements. And that's kind of why we introduce the higher level layer in this estimation formulation. So the higher level is kind of estimating the sequence of object detection events. So the idea is when the density of positive measurements for some object classifier is high enough, then we compute that as an object detection event. And then basically the trajectory can be split into the sequence of object detection events. And we can use, we model the sequence of object detection events as a hidden Markov model. And then we can use the kind of traditional hidden Markov model algorithms to compute our certainty in the sequence of object detection events being happening and given these measurements. And that certainty in the sequence of object detection events is what we use to kind of compute our switch variable priors. So when we put this together, we can actually see in the continuous time estimation, we're doing this at every time step. We're estimating the position or the pose of the vehicle at every time step. But whenever there's this kind of object detection event, we do this kind of higher level estimation problem. And we use this higher level to inform what our switch prior should be. And basically this continues until the end of the trajectory. So we want to kind of show the impact of our algorithm in simulation. So first we kind of have this method where we estimate the trajectory using traditional SLAM without these semantic measurements. And then method 1 is the maximum likelihood method, which is simpler than the second method, but it's not as robust to false positives. And then finally, we have the hierarchical formulation that can reject false positive measurements, but it's more complex. So here are some of the simulation results. So this is for a single trial, and we have a robot kind of going around the circular trajectory. And whenever it's in this blue region, it detects that it can see this object with some probability. And then these orange features are just landmarks that the agent can kind of take range measurements to. And we can see this is kind of the plot of the estimated trajectory using each of these algorithms. And we see that the methods with the semantic information have much lower squared error along the trajectory. And then we repeat this trial 100 times with randomized noise. And we kind of bin where the average squared error occurs for every trajectory, for every trial. And we also kind of bin the squared error of final position estimate. And on average, we can see that the methods with the semantic information have lower error. And then it doesn't look like there's too much of a distinction between the two methods with the semantic information, but we can kind of see that the hierarchical method has a little bit less variance in error as well. So just to summarize the second part of the talk, we had this idea of using object classifiers and a map of where those objects are located, and we introduced 2 methods for incorporating this semantic information into traditional SLAM algorithms, and then I showed the improved accuracy and robustness in simulation. So I want to kind of summarize the whole talk So in the first part of the talk, I wanted to show a framework that we use to design agent behavior in a way that guarantees safety and progress of all agents. And I provided proofs and showed the results in simulations. And then in the second part of the talk, I showed the design of an estimation algorithm that kind of encodes this semantic information. And I also showed how these results improve the accuracy and robustness of traditional SLAM algorithms. Even though we've done a lot of work, there's still a lot of work to be done. So this is kind of one potential future direction for the behavioral contracts specifically. So right now we've defined kind of these very strict contracts for one class of agents, but we kind of want to make these contracts more flexible and also be able to accommodate different agent classes, including humans. So if you include humans, then you have to kind of be able to handle unexpected behaviors and protocol violations. So kind of a direction for doing that might be, how do we design these kind of data-informed contracts that kind of lose a little bit with respect to these formal guarantees because you get these protocol violations, but gain a bit in terms of flexibility. So that's just kind of one idea. I'm also kind of very intrigued by this idea of co-design. So as I showed, the autonomy stack is kind of defined with respect to these layers, and they're kind of defined sequentially. But co-design is the idea that design choices in one module impose constraints on other modules. So how do we design components in a way that's kind of more optimized for the global system? So it might look something a little bit more like this. And then an example could be a decision-making module kind of chooses an action that allows the perception module to gain more certainty or something like that. So that concludes my talk, but I do want to say a few thank yous. So I want to thank Richard, Richard Murray. He's always been there for me throughout my PhD. And he's also been a constant source of wisdom, kindness, and humor sometimes too. And he's also just taught me how to grow as a researcher and also just as an individual. I also want to thank Sunjo. So I had 2 or 3 advisors before Sunjo, and he took me in and he gave me a project that I was really excited by. And he's also always gone above and beyond and kind of teaching me and mentoring me as well. And then I also want to thank those on my thesis committee, Manny Chandy and Joel Burdick. Also the funding that made this research kind of possible, so via Cal and AeroVironment. I also want to thank my collaborators, Tung Fan Min and Alexia Harvard, and the lab groups that I'm a part of. I also want to thank kind of the broader Caltech community, so the faculty, CMS faculty, CTLO, CCID, and Caltech Y for kind of making me feel welcome at Caltech and also supporting my interests outside of research. And then finally, my PhD has been a lot of ups, but also some downs. So I'm just thankful that I'm really thankful that my friends and family have like always been there for me, no matter what. And I couldn't have done this without them for sure. So here are just some pictures to kind of capture some fun memories at Caltech that I've had. And people always put in like when they had fun, but no one ever shows what they look like for the most part of the PhD. So I just added this picture, which my office mate captured late one night. But yeah, so that concludes my talk. Thank you so much for listening, and I'm happy to take questions.
Fantastic. Thank you, Karina. So we all applaud visually, if not audibly to you. Great. So we have a little bit of time if people have questions. The committee, of course, will have its own separate session, but if there are any questions from the audience, now is your time. You can raise your hand visually if I'm looking at all of you on the screen, or you can raise your hand Zoom-wise, and I will see it pop up. Wanya,
yeah.
Okay, thanks, Karina, for the great talk. Really enjoy it. So my question is, have you thought about combining the first part of your talk in the second part? Like put the perception modular in the protocol, like, because autonomous driving is based on deep learning based perception. So I'm thinking about if you have some ideas to put them in a unified framework, something like that.
Yeah, I think that's like a really relevant question. And I think that's what I was trying to get at with the co-design. But I think the idea with the perception module is there's a lot of uncertainty and error that can come into play with the perception module. So we have to design a protocol that's kind of more probabilistic. So you won't be able to get these absolute guarantees, but maybe you'll be able to say something more probabilistic, like with some certainty, we can guarantee that like we won't cause collision or something like that.
Thank you. Thank you.
Other questions for Karina? Okay, I don't see any visually hands raised that I can see, at least looking around the screens. Great. Okay, in that case, well, thank Karina again.